I'd like now to introduce the next speaker, Rene Ong. I spoke this morning about how SLAC had been an incubator for young physicists in theory, but of course the same thing is true in experiment. A very large number of very brilliant people have passed through this place and gone on to great things, and Renee is one of those. He came here in the 1980s. He was a graduate student at Stanford. He came up to SLAC and worked with Marty Pearl and John Jaros on actually the first precision vertex detector designed for a collider environment. And his thesis was the measurement of the B meson lifetime. After SLAC, he went to the University of Chicago, where he came under the influence of our old friend Jim Cronin. And Jim got him interested in the puzzle of the origin of the cosmic rays. And so he went into high energy astronomy, where he's now become a leader in that area. He's worked on an array of both ground-based and space-based gamma-ray telescopes. Right now, he's the spokesman for the Veritas telescope, the largest ground-based gamma-ray telescope in the United States. And he's involved in the next generation projects, CTA and GAPS. So he's an excellent person to tell us what's going to happen in the next 50 years of exploring the high-energy universe. And let's welcome him.
Great. Thank you very much, Michael, for that. And I'm just absolutely here. Okay, how's that?
Yeah. No, they're fine. I asked about that too, but.
Yes, I really have.
There. Okay, so that was very anticlimactic, wasn't it? Okay, again, thank you, Michael, for the nice introduction. And as a SLAC alum, I'm absolutely delighted to be here to tell you about a really exciting and wonderful field of research, which is using the high-energy particles, high-energy radiation that we see from space to tell us something deep about the properties of the cosmos, and also possibly about the nature of space-time and frontier particle physics. So that will be my two themes for this talk. The first being that nature is incredibly able to produce accelerators which can create particles which exceed by vast amounts what we can do here on Earth. And in fact, everywhere we look, as long as we point our telescopes long enough and deep enough, we can see TeV, GeV, TeV, and even higher energy accelerators with their beams pointed towards us. So one great theme of my talk is to understand how these objects are doing that, and how they're so efficient, and how they reach these incredible energies. The second major theme of my talk is related to the possibility that at the GeV and TeV scales, you can be very imaginative and think of ways in which to test the basic properties of the standard model, and to look for new aspects of both cosmological and particle physics signatures. And so the marriage of those two things, in some sense, the inner space and the outer space, is what makes this field so fruitful. Another very important aspect of the field is the fact that it combines cultures from particle physics community and also the astronomy and astrophysics community. And that marriage of many good things from both of those cultures is another thing that makes it so interesting and exciting at the current time. And then finally, of course, I will touch on a little bit about, to some degree, about SLAC's role in the foundations and what they've done recently in this field. And at the very end, I'll have, like Jonathan did, a one-page showing some old photos that I digitized and showing some people from the days in the 1980s. So here we have a picture of the Tycho supernovae, schematic for gamma ray burst, pair production of high-energy gamma ray off of the extragalactic background light, and finally a possible dark matter signature. So let's start then with this whole premise that if you go to new wave bands, you get new insight. And this has been a frontier aspect of the cosmos exploring the cosmos from the very early days. Whenever you go to a new wave band in the photon spectrum, for example, you get new physics, new astrophysics, and new insight in the universe. And let me take one particular very special place, a very unique place, the center of our own galaxy. There is only one such point, after all. There's only one such galaxy we live in. And here you see the galaxy is largely obscured in optical, but if you peer deep with a big telescope in infrared, you can actually track individual stars that pass around the galactic center. And this is the work of the GES group at UCLA, but there are other very good groups around the world that are doing similar work. And from the study of these star transits, which take they follow stars over a long period of time, decades in some cases, you can actually dynamically measure the mass of the black hole at the center to about 4 million solar masses. And this whole technique relies on the fact that this is a relatively quiet region. Our galaxy is dormant. It has a large black hole at the center, but it's completely dormant. And if you look in all wave bands, except for the gamma rays, you will see that to be the case. And in many cases, it's fascinating that it is so dormant, but it's in many ways not very interesting. On the other hand, when you go to GeV gamma rays, there's a blazing source. This is the Fermi lat data. And then TeV gamma rays, this is from Veritas. You see this source which has around 40 to 50% of luminosity of the strongest steady source that we know about in the universe, which is the Crab Nebula, it turns out. So here you have a complete conundrum. This emission is very intense. It's completely non-thermal. We had a nice talk this morning about synchrotron radiation. This is sort of the super high energy equivalent of that, perhaps inverse Compton emission, or perhaps decays of pi zeros. It's totally unexpected, and it's completely not understood. And we never would have discovered it. We never even appreciated that our own center of our own galaxy has something incredibly unique without having to have the power to look into the GeV and TeV gamma ray bands. Now, separately from this, quite remarkably, the center of our galaxy could be one of the best places to search for dark matter, it turns out, as Jonathan Fang mentioned earlier just before lunch. Because at the center of our galaxy, we have one of the largest concentrations of dark matter, and these dark matter particles could very well be annihilating to produce a detectable signal of gamma rays that we could see in these detectors such as Fermi or Veritas. But we have an embarrassment of riches in that there's this very strong astrophysical source there, and we know this is very likely to be an astrophysical source, and that's going to confuse things. But fortunately, the astrophysical source appears to be very point-like, consistent with being right on top of the galactic center, the massive, supermassive black hole, Sagittarius A star. And the dark matter profile is broader, big enough so that we can actually look outside of the astrophysical source and actually look for the signals from dark matter. So it's really quite remarkable that this one object actually might be able to tell us so much about the universe. So our outline then, start off with this introduction to expand on that a little bit more. Then I'll move on to the present landscape. And again, I'll do a very brief survey of the existing experiments. I should say in advance, number one, that I will talk about a number of different experiments, a little bit perhaps in more detail than some of the previous speakers, partly because that's my own area. I build instruments, and also because it's a really key ingredient of this field that we're using many of the really profound ideas and profound techniques of particle physics and applying them to do astrophysics, which astronomers generally do not understand in a general sense, these techniques. And so it's required to have this particle physics experience. And then I'll talk about the future. And we were asked to talk about the future and focus a little bit on the future, maybe in the next 50 years. I decided to be not quite so far ahead. I'm going to only go 25 years. But I will go out on a limb and make a prediction for the results to be announced at the 75th anniversary of SLAC in 25 years' time. I hope if the talk's decent enough, I might be able to come back at that time. And I hope you're all here as well. So we celebrate two great anniversaries in 2012, the 50th anniversary of SLAC, and the progression actually of SLAC from a linear accelerator library to a multidisciplinary laboratory with many great avenues of research. We also celebrate the 100th anniversary of cosmic rays that was alluded to in Andreas's talk this morning. This is a big event actually this year. Victor Hess going up in a balloon from his base in Austria to 5 kilometers and seeing quite clearly that there was a penetrating radiation of charged particles that were coming down from above. 100 years later, we have a remarkable array of instruments, CTA, IceCube, and giant air shower detectors, which are trying to still, in many cases, understand these very high energy particles. So most people in this room, I'm sure, are very familiar with the fact that the early days of cosmic rays were trying to understand their properties and also to give birth to what we now call particle physics, with the discovery of the positron here and the east-west effect there to show that they're protons. Then, around 1940, we began to realize that the cosmic rays themselves had quite remarkable properties. 1939, Pierre Auger, using the extensive air shower technique, that is a high-energy particle coming in and creating a broad swath of particles that hit the ground at once, he discovered that their single primary of cosmic rays have energies exceeding 10 to the 15th electron volts. Fermi in 49 proposed a very interesting mechanism related to shock acceleration, which we use in a different context today, but could underpin a lot of our understanding of how these cosmic accelerators work. And then finally, in 1962, John Lindsley and his collaborators at the Volcano Ranch experiment in New Mexico discovered air showers that were so large they could only be explained by 10 to the 20th electron volt particles. And so we call these the ultra high energy cosmic rays. So at the founding of SLAC in 1962, we already knew that cosmic rays were mostly charged particles, protons, and nuclei, and that they covered an enormous dynamic range of around 10 to the 12th in energy, from around 10 to the 9th, or GeV, all the way in on 10 to the 21st, or a ZeV. And here are the acronyms down here. They have they're an important source of energy in our galaxy, but unfortunately, because they're mostly charged, they're bent in the inhomogeneous magnetic field of our own galaxy. And so it was very well realized right around the time that SLAC was founded that photons and neutrinos, being undeflected by magnetic fields, can be used to directly image the astronomical sources of these particles. And so the ideas for this type of astronomy existed 50 years ago, but it took another 25 years to bear fruit. So now moving forward 25 years, the years right around 1987, that was also the year that I got my PhD from Stanford, were critical ones for gamma-ray neutrino astronomy. We had the detection by IMB and the IMB and Kamiokande water Cherenkov experiments of neutrinos from supernova in the Large Magellanic Cloud, 1987A. A small number of neutrinos, but a convincing signal. This is still the only non-solar system neutrino emitter that we know about. So it's been difficult to get more sources, but we're narrowing in on that now. And then another important result in 1989 was the detection of the first TeV, clear TeV gamma ray source by the Whipple 10-meter telescope on Mount Hopkins in southern Arizona. Here's a picture of the crab, the remnant of a supernova explosion that we observed on Earth in 1054 AD. And then finally, the launch in 1991 of the Compton Gamma Ray Observatory, a major great observatory that did an unparalleled survey of the sky and then led to a really great, significant advance in our understanding of the universe and the GeV and higher energy regime. And then for Secretary Chu, I put this in to mention that those two landmark experiments, but a little off the edge, were DOE supported and led to very, very, very important results. And a hallmark for this field actually is that you can go down an avenue, and if you're reaching new sensitivity or new energy regimes with a very promising technique, you will almost certainly see something that you didn't expect otherwise. So we shouldn't be so programmatic in how we worry about what we're going to do. So this whole idea of multi-messenger science can be pretty well encapsulated in one transparency. You have some cosmic source, perhaps an active galactic nuclei. Starting from my first slide, our own galaxy is not active. We live in a normal galaxy, a normal spiral. But these AGN may be powered by accretion onto a supermassive black hole, which then feed energy along the angular minimum axis along what we call a jet, which we can see quite readily in these objects. In many cases, they're pointed towards us, and the gamma rays and neutrinos can be detected on Earth by terrestrial detectors. and the cosmic rays will spiral to us, which we can detect maybe sometime later, and they can explain the highest energy cosmic rays. But wait, there's a difficulty, and that is particles can in principle be absorbed. And in particular, here's a plot of the power spectrum as a function of wavelength. You have the CMB here, you have ordinary starlight here, and then the re-radiation portion from the dust. These two portions down here, called the extragalactic background light, can absorb high energy photons in the hundreds of GeV and TeV regime and distort the spectrum, and in some cases absorb the photons from those distant objects completely. We'll turn that around to our advantage to actually use the distortions in these spectrums to get a measure of these primordial radiation fields, which actually are very difficult to measure but contain important information about the total luminosity of the universe and its evolution. On the other hand, the protons can interact at very, very high energies with the CMB through this process here, which creates a suppression above energies around 6 times 10 to the 19th electron volts, the so-called Greisen-Zetsepin-Kuzmin effect. Clear suppression, and also, since the CMB is omnipresent throughout the universe, this limits the distance that protons can travel to around 150 megaparsecs, and so it limits the sources of these ultra-high energy particles, again, around 10 to the 20th electron volts on up to that kind of scale. But those interactions, which should be occurring, would then give a detectable signal of neutrinos as well, which then can amplify and confirm our understanding that this actually important absorption process is happening. So then my two main scientific motivations then are this new window in the cosmos. This is what I alluded to in the beginning, and also the connection of inner space to outer space. And in particular, new physics and new particles can give detectable high energy signatures. For example, dark matter, as just discussed by Jonathan Fang, primordial black holes, axion-like particles, heavy neutrinos. You come up with a list, and then we can try to look at it at these very high energies where they might be interacting. And then the other thing that I just pointed out just on the last slide is that the high energy beams over long distances we can use that as, in some sense, like a beam dump experiment where we can see what's going on through intergalactic space and try to get some measure of what's happening in the intergalactic universe. And I have this quote from my former colleague, David Schramm. Yogi Berra was not one of my colleagues, but he's always a good source for good quotes, right? So here's the kind of one slide, detector ideas. High energy cosmic ray or gamma ray coming into the upper atmosphere, creating these extensive air showers. We can see the particles on the ground in what we call air shower arrays, either the particles themselves or the nitrogen fluorescence that they make in the atmosphere. Or we can see the Cherenkov light on dark, clear, moonless nights in large optical telescopes via the atmospheric Cherenkov technique. Satellite and balloon experiments can also look at primary radiation coming down and detect it directly. For example, the Fermi Gamma-ray Telescope in space. And then finally, neutrino experiments typically look for upward-going showers from neutrinos that go through the Earth and then give a shower in either ice or water, again using the Cherenkov technique. So moving on to the present landscape, I want to survey the existing instruments and provide just a couple of the recent scientific highlights. And I'm going to proceed in this order of gamma rays, cosmic rays, and neutrinos. And that's sort of the order in decreasing amount of confidence or decreasing amount of information that we have. Right now, I don't think it's too parochial to say that the gamma rays sort of dominate our understanding of the high energy universe at the current time. So these are the experiments now that we have. I'm obviously not going to go through all of these, but we have balloon experiments, space experiments, several large atmospheric Cherenkov telescopes, of which Veritas is one of them, several large air shower arrays, Auger and the telescope array, HAWK soon to be constructed in the TeV gamma ray band, and then a number of ice and water Cherenkov experiments. Starting with the Fermi, very close to the heart here at SLAC, it's a particle detector in space. It detects gamma rays via the pair conversion technique in a silicon strip detector. And cesium iodide calorimeter measures the energy, has a very large field of view. It's been up in orbit for about 4 years now, and this is tremendous science. I'll have a couple slides on that. SLAC had a major role in this from the very early days. I'll talk a little bit more about this in just a moment on the early days of SLAC getting into this area through all these various things. And all of these are crucial contributions not only to the LAT, but also to the entire community of astrophysicists who are using this. Actually made a very big difference and it greatly increased the science output by having such a strong laboratory presence. So here's a beautiful picture of the LAT sky taken after several years. And you see these are a counts map or a significance map, if you will, of, I think it's just a counts map of different regions of the entire sky. And this is the galactic plane here down the center. And so you see a large body of diffuse galactic emission, plus many individual sources, hundreds and hundreds of sources in the galactic plane, a much deeper and much more rich understanding than when it was afforded by the Compton Gamma-ray Observatory. Here's the galactic center. And then off of the plane, you see many extragalactic sources, AGN, galaxy clusters, the local group, for example. And then here you see the faint glow of the diffuse component. So there's actually a diffuse component of gamma rays, which we don't yet fully understand. It's very important to understand that seems to pervade isotropically the sky. Now moving on to the ground-based technique. So Fermi operates up to the sort of hundreds of GeV range, limited by the number of photons they can detect. I should have mentioned that typically these sources have falling off power law spectrum. There's a reason why that is that I can go off into the questions about. But to get to very high energies, you need a much bigger collection area. And that's afforded by this ground-based technique, atmospheric Cherenkov, where the high-energy gamma ray comes in. It creates electrons and positrons that are moving faster than the speed of light in air. So they emit Cherenkov radiation. And this Cherenkov radiation is beamed to the ground in a narrow pancake and reaches the ground in a few nanoseconds, a couple hundred meters across. And so large optical reflectors like Veritas, in this case a 12-meter diameter dish, reflect that light to a camera and then image these showers, these tremendous TeV gamma ray showers in the night sky. And if you come out to our instrument, and as a spokesperson, I heartily invite you to come out. It's very close to Tucson. You can go into the trailer and I can look on the scope and you can dial it down and you can actually see these narrow flashes that are occurring from these high energy particles that are hitting the upper atmosphere and then creating this really beautiful signal that is not mimicked by anything else in the night sky. Should mention that this technique is very sensitive but a relatively narrow field of view, but has an energy range up to tens to even hundreds of TeV. And we recently just completed a camera upgrade in just actually right now that will allow us to further extend our energy coverage and sensitivity. So this is the gamma ray sky seen by such instruments like Veritas, and there are two others that I'm not going to discuss, Hess and Magic. Large number of sources. And it may not look as impressive quite as much as Fermi, but we have to remember that there are only 2 known in 1992 and 8 in 2012. So it's just been an explosion in the number of sources and also our understanding of how they work and also the different types of sources. I'm not going to go through all the detail, but a large fraction of these are active galactic nuclei, as I mentioned, a large number of other sources along the galactic plane, and then many sources that are still not understood really at all. And so those are known as dark, unidentified, or other. That's these, and those include the galactic center that I started the talk off with. We have this very strong source in the galactic center, which we still don't really fully understand. And I had a slide on sort of theory and how these accelerators work, and I decided it was too complicated, and I would probably be running out of time at that point. So I just threw up a little more pictorial, thanks, Michael, which shows that we're investigating a large fraction of different and novel acceleration techniques in these different types of objects, in pulsars, spinning neutron stars, AGN I already mentioned, star-forming regions such as starburst galaxies, supernova remnants, often thought to be the most likely origin of the high-energy cosmic rays, very interesting binary systems, totally unexplained objects such as the galactic center, and then finally gamma ray bursts, which are the most violent explosions since the Big Bang, which could only be identified for the first time in gamma rays. So this is just sort of an encapsulation of some of the extreme astrophysics that we're probing. But I'm just going to talk about 2 particular topics in a little bit more detail, and those are supernova remnants. So not the supernova itself, but the remnant shell as it expands in interstellar medium over hundreds of years, generally very likely to be thought as the origin of the cosmic rays, certainly up to around 10 to the 14th, 10 to the 15th electron volts for reasons of energetics and luminosity. And the idea is, it goes back to this original idea by Fermi that the shock wave that comes out from the supernovae as it moves in the interstellar medium traps particles that are bounced back and forth across the shock and then can get boosted over many years to very high energies. This model is sort of the canonical picture in high energy astrophysics, and only recently now, in the last couple years, are we finally getting the experimental proof that it could actually be right. And here's some data from Fermi and Veritas on the very famous supernova originally observed by Tycho Brahe, showing the power spectrum, if you will, the spectral energy distribution for the two different wave bands, again, the space-based here and the ground-based here, with a fit to a hadronic accelerator, if you will. Hadrons in the jet, in the shock waves that are interacting with materials to create pi zeros, which then give us the gamma rays. It's not ironclad, but it's very suggestive, and more evidence is needed, but we're really on the right track, and we're really getting a handle now on the origin of these high energy particles. On the other hand, there are sometimes things happen that you just have no idea how they work. And here's an example of this, a complete surprise. The Fermi bubbles, vast plumes of energy creating gamma rays that go many, many thousands of light years up above and below the galactic disk. Don't really understand them. They have relatively sharp edges. They have a very hard spectrum. They could be related to earlier history of the galactic center when it might have been active, but we really don't know. So a real conundrum for our field. Moving on to the high energy cosmic rays, Auger is a very enormous 3,000 kilometer squared experiment in western Argentina with very high energy sensitivity, beyond 10 to the 17th electron volts, and sees the particles that come down and create showers of both, as I mentioned earlier, nitrogen fluorescence and the charged particles on the ground. This is the Auger map of high energy particles beyond 10 to the 19th, actually beyond 5.5 times 10 to the 19th electron volts. So these are the highest energy particles that we know about. And remember, these in principle could be bent if they're a little bit more local, but in practice at these energies, we think that they should point back to their origin. There's not compelling proof yet that they are pointed back to their origin, so more data is needed, but it's somewhat suggestive that they line up with matter distributions as indicated by these blue circles, which indicate positions of nearby active galactic nuclei, which again have to be within about 150 megaparsecs of us. On the other hand, the spectrum is quite clear at these very highest energies, 10 to the 20th. There is a clear rollover. And it's completely consistent with this GZK mechanism that I mentioned earlier on, the protons interacting with the cosmic microwave background radiation, but it's not completely ironclad yet. That's the only explanation. The accelerators themselves could be running out of steam at these energies. And then finally, the IceCube neutrino detector at the South Pole, really monumental effort of about 5,000 phototubes buried deep under the South Pole ice. Here's some detail of how they heat up water and force it down a hole to melt the ice and then lower the photomultiplier tubes. Just recently completed, the largest neutrino detector ever built, most sensitive one too. So far, they haven't seen unambiguous evidence for any point sources. And this plot here shows a probability map. So you see some clusterings, but they're all they have probabilities which are above what we would like them to be in terms of being significant. So there's no significant detections yet from IceCube. But they do when they look at the very highest energies and look anywhere in the sky. They have two detected events with a background of 0.14. This was announced this year. Again, not statistically significant yet. But these, in principle, could be consistent with GZK neutrinos. Here shows where these two events lie in sort of an energy plot here, and these curves correspond to various models, and these other shaded curves correspond to the background. So again, it's early days, but IceCube is functioning well, and it would be great if the neutrino sector could come up with the gamma ray sector and have a similar number of sources and similar type of understanding of the universe. And then moving on to the connection between inner space and outer space, I'm only going to really talk much in some detail about dark matter. Jonathan already motivated the fact that dark matter is omnipresent, an important component of the universe, and one very interesting and very important avenue of searching for it is looking for it in the cosmos. And the other thing I'm going to mention is a little bit about the extragalactic background light. I might have to cut that. So this was similar to what Jonathan showed, that the dark matter signal WIMP annihilation signal can be factorized to what you see can be factorized into two components, one relating to the astrophysics and one relating to the particle physics. And this is really beautiful because if this technique works, which we have good reason to believe that it might, we could then actually not only see the dark matter interacting through its particle properties, not through its gravitational properties, but we could map its structure in the universe, which is pretty outstanding, actually. And so it's obvious that it's an avenue which has to be pursued if the payoff is so huge. Neutrinos can also do this for those neutrinos that thermally coalesce inside our sun, for example, where there's a detectable signal as well. And this shows a simulation of the dark matter annihilation signal that could give GeV or TeV gamma rays, large concentration in the galactic center, but also satellite galaxies, dwarf satellite galaxies in particular, near our own galaxy, and also extragalactic sources such as galaxy clusters. Now, one key nature of some of these signatures actually are that you would see distinct line signatures that are associated with particular properties of, in this case, the weakly interacting massive particle. So in an experiment like Fermi, where you can actually have the energy resolution to look for lines, and perhaps eventually on the ground as well, you could actually try to reconstruct that line and actually do particle physics in space, which would be quite remarkable. So here are the current limits. Jonathan showed a similar slide a little while ago in the cross-section, average cross-section times velocity on this axis here as a function of the weakly interacting massive particle here. And you see the Fermi limits here, and these are the limits from the atmospheric Cherenkov telescopes. You can see they're pushing down to the same regime. So a large fraction of models are already starting to be excluded. This is really good news. We're now getting to the point where we, in principle, could have a dark matter detection around the corner. That would be amazing. That wasn't the case 5 years ago, 8 years ago. So we're very similar to the direct detection experiments where we're really starting to probe interesting parts of physical parameter space. And another key thing is that we're now reaching the thermal limit that he mentioned, that is, if the dark matter is the particle that he discussed. On the other hand, those are limits which are well-founded and well-established. There are also very interesting signals similar to what Jonathan showed about the light mass WIMPs. And here from the Fermi data showing not completely statistically significant, but interesting signal very close to the galactic center, which is about a little over 3 standard deviations post-trials, and would be a WIMP annihilation line at 130 GeV. And this has been seen by several different authors, so it's almost certainly a real effect, but it may be a systematic effect. We're not fully sure on that. It needs to be explored. But the fact that it's close to the galactic center and the fact that it's right in the mass region where we're interested and it's sort of what we were looking for makes it very intriguing. The good news is that this can be confirmed or refuted. Fermi will continue to still operate, and we'll do a much better job over the next few years of understanding if this is true or not. So because the dark matter is a constant source, it won't go away. So that's good. It should always be present. I think I'm going to skip this, so I just have to move on. So let me just discuss the SLAC program a little bit. Starting in the early 1990s, Elliot Bloom got involved in the USA X-ray mission. And then around 92, there was this convergence of Bill Atwood, Elliot, and Peter Michelson with the idea of a new gamma-ray instrument to replace the Compton Gamma-ray Observatory. And this led to the GLASS concept, which later became Fermi. And there was a very nice workshop that Elliot hosted in Stanford in 1994 that gave birth to a lot of the big ideas behind the mission of GLASS. And I should say, and this is really true, that the directors really were enlightened and had a very good role in nurturing and supporting this program. And of course, it goes without saying that there's a very important connection here at SLAC with Stanford, and the fact that Peter Michelson was involved in the Compton Gamma-ray Observatory, and he had worked with Bob Hofstadter, who had originally designed that instrument and got the whole area involved in this research. And so the significant impacts so far, and there are more, the origin of the LAT and the successful operations in science from Fermi, some critical work which I'll mention in just a moment to demonstrate something called the Ascarian effect. I'll discuss that in just a moment. Theory, of course, the present development of the Cherenkov Telescope Array. And I should say that there's a very, very important astrophysics component here at SLAC, which I'm not talking about. It's not really in my purview, which is the Large Synoptic Survey Telescope, a very important mission for dark energy It's just not in my area of research, so I didn't put it in the talk. There's just too much to cover. So here's a talk, here's a copy of a transparency, if you can believe I save these things occasionally, from a talk that I gave here 20 years ago in March of 1992, excuse me, on almost the same topic. Okay? I'd been in the field for a couple of years. At that time, I got a lot of good questions from people. And it was very fertile. And it was right around that time, I think, that Elliot Bloom and Peter Michelson and Bill Atwood had this convergence and began to get going. I'm not responsible for that convergence, but it's just that we were thinking along the same kind of lines. And this led to the development of the LAT, and this is that workshop that happened in '94. And then the power of Fermi and all the great results that you see. Now, something totally separate was this very interesting idea that very high energy neutrinos could coherently produce Cherenkov radiation, which then could be detected. And this was actually brought to realization in a project called ANITA, which is actually a balloon-borne experiment looking down on the ice, on the Antarctic ice, for neutrinos that go sideways, create Cherenkov radiation, and then the radio Cherenkov radiation is detected by the ANITA balloon experiment. But that whole thing wouldn't have happened if the whole idea behind this effect, called the Askaryan effect, which is the coherent production of the radio Cherenkov emission, hadn't been demonstrated and proven here at SLAC through a series of beam tests in end station A of the LINAC, starting with sand in 2000, rock salt in 2004, and then finally with ice in 2007, where the actual NITA payload was calibrated. And here you see some pictures of people who played important roles in that effort. And then finally, in the last 5 minutes or so, I want to go on to the future. I was supposed to concentrate on the future, but it's very difficult to spend all your time speculating. But I did some speculating, so we'll get to that, and we'll talk about the science results presented at the SLAC 75th anniversary. So here are my questions. We're not going to go through all of them, but they're big questions. What is dark matter? What new particles and interactions can be identified? What are the origin of cosmic rays over the entire spectrum? What is the maximum energy of cosmic particle acceleration? What are these intergalactic radiation fields and how are they produced? Is there an isotropic neutrino flux? And just in general, my first point, getting back to how these objects actually work, how these potent accelerators work, and what is happening at the galactic center. I mean, how can this region, which is so quiet in other wave bands, be so powerful in the high energies? And here's just a long, sort of a shopping list of what we need to go forward. This is sort of a very subjective, of course. And one key thing you see here is sensitivity. Whenever you go deeper with any instrument, astrophysically, you see new phenomena. It's always the case. It's sort of like the high luminosity. So if you have a 4 sigma Higgs detector, but you can go immediately to 10 times the data set or 100 times the data set, you would do it. I mean, you could do that. And so that's our sort of coin of the realm. We don't need to go to higher energies in this field because we already know that so many of the interesting phenomena are already in our band. So we don't really have an energy frontier, but we do have an intensity frontier. And then the future efforts then, in the gamma ray sector, the world's community has coalesced around one project called the Cherenkov Telescope Array. The cosmic ray community, it's not quite clear. The only really ongoing project for the future that we know about that I'll briefly discuss in one slide is something called GEM-USO, which is an orbiting space experiment. And the neutrino sector has many different options, and they involve radio detection, a very large Mediterranean experiment, which I won't discuss, and a lower energy extension to IceCube, which then could do neutrino oscillation studies, quite interesting, but I won't have time to cover them. CTA. Very important mission, much more sensitive than our existing instruments, wide field of view, 2 sites. And here's sort of the critical slide, the take-home message that CTA will really push down our understanding of our ability to search for weakly interacting massive particles, dark matter, to well below the thermal line that Jonathan Feng mentioned. The US has a major role to play in CTA through a design of a much more advanced telescope, a 2-mirror design, which will have much higher resolution, wider field of view, and much better spatial resolution. Also very important is that we're exploring sites in northern Arizona here near Flagstaff as possible hosts for one of the 2 CTA sites. So again, this is a very advanced super version of Veritas, if you will, using the atmospheric Cherenkov technique. There's some details on the telescope. The camera, to be developed to a large extent with contributions from SLAC, could be a major factor in SLAC's future. GEM-USO, space mission looking down at the highest energy cosmic ray. So like Auger, but looking down now at the highest energies. This is sort of a huge collection area that they have via the nitrogen fluorescence technique. It's being thought of very highly. It's in phase B in some other countries. The earliest it could launch is probably around 2017. And then finally, extensions to IceCube, such as a radio Cherenkov. As I mentioned already, we had this Ascarian effect, which clearly indicated you could build large detectors to detect neutrinos via the radio technique. And this is the idea. Here's IceCube, that kilometer cubed experiment, now tiny over here. And here are the spacings for a radio neutrino detector, which would be much, much larger and could detect in much greater probability these so-called GZK neutrinos beyond 10 to the 17th. So the future role of SLAC is pretty clear. Very strong science base. SLAC has a history of excellent interdisciplinary approach. The HEP technical expertise is very important, as demonstrated in Fermi. Beams are still very important, as demonstrated by the ANITA experience. And then other very important aspects of being a national lab. And now, my predictions to conclude for what we will see in 25 years. Dark matter will be discovered in VHE gamma rays, and we will be able to map the galactic dark matter distribution through its gamma ray signature and actually detect proper motion of a nearby clump. That is certainly possible in the next 25 years. We'll detect 25,000 neutrinos from a supernova in our galaxy in Cygnus at a distance of 7.5 kiloparsecs. This will provide confirmation of the neutrino hierarchy, as well as unbelievable information about how supernovae work. We actually do not know how supernovae explode at the current time. The models do not work. So we need these neutrinos. 3 local sources of positrons will be identified, which will solve the mystery of the excess positron flux at high energies that Jonathan mentioned. We'll do an actual first measurement of the intergalactic magnetic field via a high energy absorption technique. And the density and distribution of those fields will argue for a primordial B field, which cosmology can't explain actually right now. The GZK effect will formally be established and will identify the sources. And the origin of the cosmic rays, we may be the closest to this one, that census of 300 galactic sources and gamma rays and 40 sources detected neutrinos will give us the measurement to establish 90% of the origin of the cosmic ray flux. Certainly possible that could be done in the next 25 years. And then finally, we can make a precision measurement of electrogalactic background light, the full luminosity history of the universe, again, through this absorption technique. So that would be really something if we could do those things. And I think that's actually achievable in 25 years. And these are known topics. Of course, there's going to be something unknown, right? I mean, that's the whole point of doing science, is that we're going to probably see something that we never expected. So my second to last slide then is something related to the personal aspect and about how important SLAC was in my own career. I worked again in a really wonderful experiment called Mark II. I see many of my Mark II collaborators here. As Jonathan mentioned, it was not only a very fertile place, but also we had great visitors from outside that contributed greatly to the intellectual power. And in particular, I was fortunate enough to work in a relatively small group led by John Gels that built the first precision vertex chamber that was at the Mark II experiment at PEP, and we did these lifetime measurements. And this was a tremendous group. I worked with John in Martin Pearl's group. The spokesman of the collaboration was Jonathan Dorfan, and Bert was sort of our honorary spokesman. And God forbid you were sleeping at 7 in the morning on an owl shift when Bert showed up to see if the experiment was running. Of course, we really feared more likely that Marty Breidenbach would come down and ask us which cable was unplugged. But that was great training. And the other aspect of the training was that you invariably meet many young people, and you learn as much from your cohort, or your graduate student cohort, as you do from senior people. I'm sorry to admit that, but it's really true. And we had really tremendous younger people that I learned an enormous amount from. And in my class, there was myself and Pat Burkett, Robert Johnson, and Harry Nelson. In the class before me, it was Larry Gladney and John Butler. in the class after me, Natalie Rowe, Dean Carlin, Keith Ryle, Spencer Klein. And on the small projects that I was working with personally, we had outstanding postdocs, Nigel Lockyer, Jim Alexander, Charles Munger, and our current director, Persis Drell. And so here's some pictures of just the graduate student days. As Jonathan mentioned, we're all much younger then, but here you see myself with Nigel and Mark Nelson, Larry Gladney, who's at Penn, David Bennett, and Robert Johnson. And here's Elliot with Harry Nelson at his graduation. I don't have a picture from my own graduation, which sort of annoyed me, but I couldn't find that. And here's Pat Burkett here. So these are mostly students from my class, and many of them are here, so I congratulate you for returning to SLAC. So to summarize then, high-energy particles probe the astrophysics of TeV, PeV, and even EeV particle acceleration in the cosmos not tested or understood by any other means. And equally important is using high-energy probes to search for new physics beyond the standard model in an energy region which is of interest. 100 GeV WIMPs are very interesting. That's the region where we need to be, and we can probe that with these instruments. The current suite of instruments provide an unparalleled view of the universe, but still, obviously, when you get such successes, you raise as many questions as you answer. And so we have many questions to answer still. And then finally, and most importantly, again, congratulations, SLAC, on 50 years. I look forward to another great 50 years. It's developed a world-leading program in high-energy particle astrophysics. And as I tried to mention, the Cherenkov Telescope Array is a unique opportunity, a very powerful instrument in which SLAC can play a key role in the near and further future. Thank you.
So thank you very much. Questions for Renee? Go ahead.
Going back to the Tycho spectrum that you showed, could it be if that was really what you were seeing, if you were really seeing acceleration there? Could you learn anything about the symmetry of the explosion from the power spectrum?
OK, I don't need to show that plot to answer that question. Not yet. Not yet. But eventually data could do that. I mean, we know quite a bit about the explosion from other wave bands already. So that picture was an X-ray picture. So we know it's, these young supernova, which we're seeing, are sort of very clean, and that's why Tycho is a good example. The older supernova are typically interacting with material, also maybe hadron accelerators, but they tend to be a little more complicated. But I can chat with you a little bit more about that.
OK, one more question? OK, well, thank you very much.